well, first of all, obviously I'm not Maria Girone. She's my supervisor, but unfortunately can't be here today, so I'm stepping in for her to talk a little bit about the computing challenges and a little bit about what openlab is doing to address some of these. So I'll start by doing a little bit of background here on to motivate the challenges we're facing, and apologize if you've been following the lecture series, like the general summer student lecture series that are in the mornings. You might have heard some of this before. If not, I'll try and be as concise as possible here. So, okay, we went through this. So, in general, CERN's mission statement, as Alberto and Enrique before him said, is in general to try and find answers to some of the most fundamental questions in physics. And we do this by studying the small, the things that are no longer possible without high energies in physics. So this is looking at subatomic particles and moments right after the Big Bang. The way that we do this, of course, is with statistics and a lot of data. So you probably know some of this. The main accelerator, the LHC complex, is made up of 4 experiments. 2 of these are general experiments, which you see across from each other on the presentation here. It's CMS and ATLAS. And then there are 2 more specialized experiments, which are LHCb and ALICE. And I'll go briefly through what each of these is doing here. But the LHC itself is about 100 meters underground. It's 27 kilometers in diameter. And hopefully, in the near future, will be the Future Circular Collider, which will up this in every order of magnitude. So the machine that we are operating here is kind of incredible. It's a first in a lot of things. The collision points are some of the hottest on Earth. The cryogenics are much colder than outer space. The magnetics, I have no idea what the records are now, but they are some of the most incredible superconducting and magnetic force ever constructed. Like, for example, if at the CMS experiment there's a toroidal magnet there that if you were to have a scatter plot of every magnet ever constructed, they're all kind of grouped around here, and then the CMS magnet is way up here. It's kind of amazing, just that part alone. That's ignoring everything else that's going on at this experiment. So it's really an incredible thing in a lot of different areas, and these are just the physics experiments. There are many other experiments at CERN that are not on the LHC line itself, such as Medicis and the fixed target system or fixed target experiments in other parts of the CERN campus. So, as I said, the 2 general purpose experiments are ATLAS and CMS. Since there is only one of these machines in the world, the way that they're constructed is a bit unique. The experiments maintain a sort of communication silo between them. So they don't share any common design or communication about what they're doing or how they're operating their detectors. So that and this is exactly because there is one of these machines, if you think you have a discovery at one of these detectors, the only way we can have experimental confirmation of your finding is that you also see it somewhere else, and they know nothing about how you found it or what sort of software or machinery you're using for that purpose. So it's kind of amazing that we are able to still be coming out with new theories that are confirmed on the same machine, but independently. ATLAS, which is the one that's across the street here on the Mehran site, is, as you can see here, it's about 7,000 tons and massive machine. If you get the opportunity here, well, for any of these experiments, try and go along on a tour and visit one of these machines because they're breathtaking to see in person. CMS, which is at 1.5 on the ring on the opposite side in Cessy in France. Is a little bit shorter, but massively heavy. The superconducting solenoid magnet there makes up about 90% of the weight of it. It's 14,000 tons. And I already spoke a little bit about this, but these are two general purpose detectors. I'll talk a bit about how these work, but I'll continue here and circle back to this. The other two experiments, as I said, are ATLAS and LHCb. ALICE and LHCb. I always mix this up. But ALICE is looking at the gluon plasma state, which is moments after the Big Bang, and sort of physics that existed at that time before things rapidly cooled off. And LHCb is looking at the quark-antiquark bindings, or matter and antimatter. So really looking at the question of why do we exist? Why is there more, as we understand it, more matter in the universe right now than antimatter? And where does this asymmetry come from? So these are the four major experiments on the LHC. As I mentioned, there's, I think, 14 or I've lost track now, but many more experiments that are also on the CERN beam complex, let's say. Some of them come off of the proton synchrotron, some of them are off the super proton synchrotron, or SPS. Depends on the type of particle they're using for their experiments. So now you know a little bit about what detectors exist here. Let's look at the interesting stuff. You guys are in computer science mostly, so how do we read these things out? They, for the most part, operate like a standard camera. You have, if you know anything about digital cameras, you have a sort of sensor on the back. You can take a snapshot and record what those sensors had for charge or light at some moment. And that's, in general, how most of the detector or physics at least detector readout technology works. You either directly are recording charge on some sort of sensor, or you're converting particle action into light, which then you can see with the sensor and record this. The only difference is we take these photos much faster than any camera you've ever seen. So the nominal frequency of the LHC is around 40 megahertz, and we are, every time the beam is going through, we have a trigger system, which is kind of like what you would think when you snap the button on a camera. This is about 40 million times a second, and the standard, let's say, megapixels of a camera, imagine that with several orders of magnitude. So that produces an enormous amount of data. In fact, I should have gone to this slide. It's more data than we could possibly read out. Even if we had a more or less unlimited budget, there's no way to store or move this amount of data. So we have to cut this down into something that's much more manageable. And all the experiments do this in a little bit different way, but the general method is you need to have some fast filtering. So you have the raw readout, which I guess, for the example Maria's got here from ATLAS, you have the 40 megahertz signal, which if you were to read out all the channels and try and store that, it's in the order of petabytes per second. I don't know how familiar you are with today's SSDs, but they're not close, even if you had a server-sized rack of these. So generally, this is cut down first with a hardware trigger or level 1 trigger, which is throwing away all the events that either aren't interesting, aren't in time, or maybe we already know about this sort of phenomenon and we don't care to keep it anymore. What's left after that is already a cut in order of magnitude, so we're down to the terabyte per second demand, and this goes to a level 2 trigger, or the sort of software trigger, where now we have things that met the sort of fast filter requirement to take a second look at. These get passed off to software, and you have decision made on the sort of event you might be looking for, or the collision mode, like if you're in, let's say you have lead ions in the LHC at that time, you might be looking for a different type of events than what you would otherwise be searching for. So you have a little bit more involved decision process here, but the result is the same. We cut down the order of magnitude for, let's say, throughput from the detectors. So that being said, we're still at the sort of scale that, well, we are in trouble here if we're trying to do this for every experiment at CERN. So a little bit about, now we have an idea of one experiment's data demands. How do we handle this in the IT department? On IT side is computer scientists, computer engineers, and that brings us to where we are here in the IT department. This is Building 31. I think Christina said you haven't been to the IT, or haven't been to the data center yet?
Some of you saw it through the window yesterday, but we haven't done the official visit yet.
Okay, so I think you will, as far as I understand. But that's in the building next door, 513, which is the main data center. A second one is actually in construction at the Prevesan site, but that's not going to be done for another year or so. A little bit about how this works. As I said, the experiments are sort of standalone. They've developed their whole software stacks independently. Some of you maybe have already taken a look at them. They're enormous. They're tens of millions of lines of code, generally built or I say built, but grown is a more accurate term, over the past 30, 40 years. Cumulatively, features have been added, improvements made, but they're enormous code bases. And this is what's used to parse all of the data that's coming out of each detector. So what we then need to do is, we have these streams coming from the experiment. It's the job of the data center here to collect this, compress it, split it up into reasonable, logical partitions, and parse this in some way. And there's a reference here for the excellent series that's been going on. It was this morning and yesterday by Paul, which he goes into much more detail about how this is done, and how physicists really are using these data sets to do analysis and come to conclusions. But really, this is even after several orders of magnitude of cutting stuff and throwing really 90% of the data away at this point, we're still left with a really massive amount of data that we have to do something about. So we've got it to the IT department, we've got it to the central server here. What's next? This is more than we can reasonably store, and especially, as I'll come to in the future runs here, it's going to be problematic as things get upgraded. So the solution for this, what was devised over the last decades, is a global network of computing centers. This is the Worldwide LHC Computing Grid, or WLCG. And you can think of this as a bit like a directed graph of computing centers or server farms or storage farms. And it's a network of collaborating institutes. Some of them are laboratories, universities, states, that are all on the LHC network. At some point, it was a private fiber network built and designed specifically for sending physics data, because at that time, the fiber optics didn't exist to send this much data very far. And still, this is an ongoing thing, but I'm getting distracted here. But it's WLCG is a tiered network of computing centers that share their peer sites, their computation centers, and it's a method of really storing and processing a truly massive volume of data for physicists all over the globe. As you probably know, CERN is I think around 16,000 collaborating scientists, engineers, physicists. And on site here, obviously, we're not that many. It's maybe 3,000 to 5,000 on a given workday. So there's many more times the amount of people you would ever see on site here still working with the data that CERN is producing or the hardware at CERN. So the grid, in addition to processing this data, doing reconstruction, simulation, analysis jobs, works as a storage and distribution system for physicists and engineers in their home countries, or in a way that it would be otherwise impossible for all of this data to be served from a central location. So, I guess, yeah, here's a bit more details here. She's got that, it's 170 computing centers in 42 countries. I guess she's got some statistics here. I'll leave this to you to look through, and the presentation is also available afterwards. But it's a distributed network. If you were to try and look at all of the computing sites combined, it would definitely be one of the most powerful computers in the world. So let's talk a little bit about why we have this much data. As if you've been following the lecture series from the summer student program, you know that especially for exotic physics or rare events, the frequency of this occurring is extremely small. So we need a ton of data. If it only happens once in a billion or a trillion collisions, then you need a ton of data to try and find these rare events. So that means a lot of statistics. So the machine needs to be running for a long time at as high of collision rate as possible. And every time that CERN goes into a shutdown period, an upgrade period, we are increasing this going forward to try and search for this, to enable higher energies and new areas, new frontiers of physics for fundamental. So a little bit about where we are now. I've talked about stuff that's already existing in the past. Now let's look a little bit in the future. We are, well, as Enrique said, we're about to start run 3. I'm not sure what time it's going to be officially, but run 3 will go for, I think, 3.5 years, something like this. It might have been adjusted, but nominally that's the target for this, and then we'll enter another long, so-called long shutdown or upgrade period. And then the run 4, or what is commonly called high luminosity, will begin, I believe, now in 2029. This is the final hurrah, or the final run for the LHC at its current intended design purpose. Now, everything about what's going to happen in the high lumi era of LHC is problematic. Pretty much every measurable metric of the machine will be upgraded, and this has got a lot of people a bit nervous. So the frequency of the machine will be much higher. The detectors will all be upgraded. So let's say if you were to use the camera analogy, the pixel density or the amount of readout channels you have per detector is going to go up in an order of magnitude. So you have higher energy particles colliding at a much more higher frequency, and you have a much higher resolution picture of what's happening. So, and you're going up an order of magnitude in each of those. This causes a kind of blow up of the computing requirements. So what that looks like, these I think are the more recent model predictions. I don't know if you can see the bottom curve here on this. This is a sort of projected computing needs as you go in 2026, 2030, and so on. And right around here, 2029, 2030 is high lumi era. We're about 10 times higher than we could foreseeably meet even with annual improvements in CPU efficiency, budget increases, and things like this. So, yeah, when these predictions came out, the logical reaction is panic. Yeah, oh no, because the last thing you want to do is convince all the national member countries to spend a bunch of money on taxpayer funds to make a very expensive machine, and then we have to turn it off or turn parts of it off because we can't figure out how to read it out. It's too high of too much data coming out for us to feasibly control or to store or to transfer. So, as you can imagine, if you're thinking about what do I do now, this problem is being attacked from every direction possible. So, for computing needs, this means several different things. So, we need more aggressive filtering. That's one option. Try and reduce the event size or the complexity of the event, or try and change our code base. We have a really sort of inherited analysis framework that's unique on each of the experiments. Maybe this can be improved. We can use the machines in more efficient ways, and also take advantage of new and emerging technology and how we process this. And that's, I think, what most of you will be working with is how do we leverage the sort of new emerging computing resources that have never been used. Up until this point, CERN's computing architecture, for the most part, has been extremely homogeneous. Throughout the 90s, 2000s, and up until recently, it's been more or less Intel x86 CPUs. It was originally 32-bit, 2, maybe 4 cores. There was no such thing as hyper-threading or multi-parallel things, and for the most part, a lot of that code base still exists and is still used. Nowadays, of course, this sounds kind of crazy to talk about because we have things like GPUs and FPGAs and even more exotic accelerators than this. But we need to find a way to, so this is the point, is that we have a massive computing problem that needs to have an answer, or needs to at least try and be answered by high Lumi. And this is probably one of the most exciting areas or angles to try and address this problem. So a bit about openlab. I think I'll go somewhat quickly through this since Alberto covered most of it in the previous slide, but the overview is, in general, evaluating new and emerging technologies, as I said. We get to test some of these technologies in a CERN sort of or high energy physics or big data context, a sort of use case that is unique in the world for the amount of data and the speed, or let's say the throughput of processing that needs to be done. And also, well, the whole reason that all of you are here is to train the next generation, to be able to take techniques that are just now emerging as critical at CERN and will be used or needed in industry later in coming years. And of course, as you're here, I'm sure you'll all have the chance to collaborate both within CERN and hopefully without, with external companies and groups that are participating in this research today. So, as Alberto mentioned, created at the start of LHC, so just over 20 years ago, and it's really taken off as an excellent project. I will go ahead and skip this one since this was previously covered. Some of the projects, I don't know if he showed this. Wow. Okay, that's a little bit difficult to see on here, but this is just an example of some of the different projects that are under the four main themes of openlab here. So in exascale, we're looking at HPC collaboration, working with the WLCG and some of the AI and and HPC European projects. I can't even read this. The Ellis program for the AI, the Quantum Technology Initiative here at CERN for QTI, and Biodynamo, CERN for open data under the multi-sciences collaboration. So I think most of you probably find yourself on this chart somewhere, but just to give you an idea of what your fellow students might be working on and how that's related to the relationships at openlab. So I think you guys all have gotten the links for the summer student lecture program. This is just a reminder that up here, these are the openlab lecture program, where you're at now in the afternoon. There's the parallel program, the general summer student program, which of course you can also follow these. The general summer student lecture program, these are online only. Some students are gathering to watch them in a room like this, but they're only on only on Zoom. But they have complimentary lecturers. So please check out both, and as well, they're both recorded, I believe. So you should be able to, well, selectively. There's a few of them that we don't record for sensitive nature of the talk, but in general.
Actually, we do.
Okay.
We took out the sensitive stuff.
Okay. So then I take that back. They will all be available for watching later if you can't attend. But I highly encourage you to, because in general, aside from me, these lectures are given by the experts in their field. People have been doing this for their entire career. So there's really no better person to get an introduction or a higher level discussion about some of these topics. So please take advantage of them. So I'll talk a bit about, I think I've got a few minutes. Yeah, okay. We're doing okay, I think. So I'll talk a little bit about the exascale computing, which is what Maria's sort of the branch that she's leading here in openlab. And she's got 2 references here for talks for accelerators that are going to be later this month from Stefan and Marco on FPGA and GPUs, which I encourage you to check out in a couple weeks. At the moment, GPU accelerators are really dominating the growth in computing power. You've got a graph here of sort of the performance over the last couple decades of per CPU, single-threaded performance, and GPUs. Now, GPU for compute reasons is a relatively new thing, so it's still on this sort of more-ish path for performance, whereas on CPUs, we are kind of running into, it's been discussion over the years, the end of Moore's law. Can we keep doubling performance at this rate? And it's been indications now for several years that this is going to sort of plateau off. And because at some point you can't make transistor gates or logic gates that much smaller on silicon die. So the other approach to this has been with GPUs. So instead of having 24, 48, 64 cores on a CPU, you can parallelize and get maybe 6, 7, 8,000 cores parallelization, which is what GPUs do. And for the LHC, this is fantastic. The core, let's say, algorithm or the main logic loop for most of the LHC or high energy physics code is trivially simple. You have some input data from a detector. You run a small reconstruction loop on a small matrix set, but we just need to do it trillions and trillions and trillions of times. So that's perfect for GPUs. We can use them in massively parallel ways that is just not feasible with a, it seems weird to say this in 2022, but relatively limited system of maybe 120-something core CPU. A single GPU gives you orders of magnitude more than that. So this is a really interesting way to go for, especially for physics, because it's for our computation needs, it can really benefit from massive parallelization that you get in GPUs. And this is being looked at. I know some of you are looking at the machine learning frameworks. Many groups and experiments at CERN are dumping resources into trying to figure out how to capitalize from this opportunity. And also from the energy perspective. I think, I can't really see this super well, but I believe this is a chart of some of the accelerators that are out at the moment. The interesting thing to me is looking at the energy efficiency. Not only are these devices cheaper, more compact, and can do much more events per second because of the number of cores and matrix operations they can do, they're much more energy efficient, which is certainly going to be a priority going forward. How do we use less resources to do more work? I think, there's got a couple of GPUs on here as well as some of the, looks like FPGAs or AI accelerator FPGAs. Yeah. So a bit about HPC. This is, of course, where we nowadays find most of these accelerators. Countries for years, well, it's been, let's say, a competition in some ways. Countries have been investing lots of money into national computing centers, research labs, universities, sometimes they're national laboratories. And really this is where we find all of these sort of emerging technologies. The massive parallelization, compute accelerators, and large-scale storage and capacity. So one of the ideas to try and meet the high luminosity compute, let's say, gap, is to collaborate and try and take advantage of these computing centers. They've been built all around Europe and the world, and there's a possibility that if there's some gap in time when one of these machines is sitting idle, we could go in and opportunistically use a couple hour or a day slice or something of these facilities. Now, since they are in general have much more modern hardware and much newer accelerators and technologies, this is something that begins to be very interesting. So I guess she's got an example here of some of the top 10, I think, HPC systems in Europe. All of them, the majority, well, I don't think all of them, no, not 10, but almost all of them, the majority of their throughput petaflop metric is in accelerators, so GPUs and FPGAs. I think so it's interesting to see where the investment is outside of CERN, and not just high energy physics, but in industry and other sciences as well. And that brings us to exascale, which is exascale technologies. Well, I think this comes up in a minute, but okay. The projects for exascale that we're working on currently in openlab, the first is RAISE, which is the Center of Excellence. This is a EU Horizon project, so looking at AI exploitation across industries and also in research, where CERN is one of the compute, let's say, data-driven use cases for this. There are others such as reactive flow simulation. You have some manufacturing process use cases. For CERN, we're looking at how can we do work with our data sets. So looking at particle identification in experiments. So a bit about that specific use case. The application is called MLPF, or let's say machine learned particle flow. This is from the CMS experiment. So they are looking to increase the speed of identification while also increasing accuracy and reducing compute requirements, of course. We've been involved in this, I think, for about 1.5 years or 2 years so far. So she's got a couple plots here of really the scaling that you get here. So it's a little bit better than linear. I'll go forward one slide here. So if you are to scale something up, let's say in a typical supercomputing center using one process that's split across many nodes, the theoretical scaling, which is got here shown as a dashed line, you ideally want to be as close to that as possible. So here I think MLPF, he's got it shown up to about 26 nodes at the same time. So it's quite close to the ideal case. But the benefit is, if I go back a slide, so not only do you have a close to linear scaling, so the speed and throughput of this, but it actually also increases the accuracy. So you're reducing loss, which is part of hypertuning, if anyone is studying this part. But so this is a very lucrative use here for CERN's physics needs. Go forward. Okay, I think this is a bit about what I said before. Yeah, that. Okay, I'm not sure why this is on there, but yeah. So the plot on the right here, I think, is more or less saying what I was just speaking about before, is that you get better tune-up or better speed-up, let's say, by increasing the number of parallel copies or parallel nodes and scaling rather than launching individual copies. Another part of that is looking at, sorry, that was loud, looking at benchmarking. So how can we understand these parallel workloads as we scale them up? We've got a lot of experience working with traditional CPU software. And I mean, okay, our understanding of scaling of these things was you have a 4-thread process, and we just add more threads. If you've got a 20-core processor, then you can have 5 of these processes, and that's scaling. The sort of what we would call naively parallel in a supercomputing sense, or trivially parallel. But that's not the case on HPC, because these nodes are all linked to each other. You can sometimes read directly the memory from another machine's graphics card or another machine's RAM without ever needing to transfer this into the node you're on. So these machines don't scale in the same way. And in fact, some of the support solutions that you otherwise don't have to worry about, like storage and network, also don't behave in the same way. You know, it's pretty easy to model when you're on a single node, but what happens when you are spread across 200 nodes or 1,000 nodes? So this is something we are learning how to efficiently exploit. And I think I've got a backup slide on how you can access, and I'm sure some of you will be using HPC sites this summer. This is a bit about the constellation of some of the HPC sites that are available in Europe. I think these are covered in previous ones, but some of the major ones, the Jewel system, which is the exascale, or will shortly be the exascale system in Europe, so exabyte computing. Experiments have all been using HPC or working to take advantage of HPC for some time. This is an example from CMS, I think 10 million core hours on CPUs, but this is quickly transitioning to accelerators. The other topics in OpenLab, machine learning and quantum, will be covered in the next coming weeks by Sophia and Jean Roche for quantum and quantum hybrid machine learning, where CERN has certainly been working in previous years and will continue to. And I can't even read this, but I leave this here. I think I'm running a bit short on time, so I'm going to go quickly through this. And as Alberto mentioned, the upcoming topics in the future, neomorphic computing and extreme scale, exabyte, exascale computing, certainly from the high Lumi period and after. Quantum, I think the first quantum system has been installed in Europe. It's a quantum annealer at Jülich, which is the exascale HPC site in Germany. And certainly gate systems like those from Google or IBM or Rigetti. So, and I know several of you will probably be working with that. I think I mentioned a couple times, this is a little bit the roadmap in Europe for quantum. This is largely from the Jülich Supercomputing Center. All of this more or less exists today. The quantum module just came online in the past month or two ago, I think, so very new stuff. Okay, so I think I'm out of time here. I'll wrap up. So hopefully I've given you a somewhat rapid overview of where we've been before, the problems we're facing, and some of the ideas to try and address it. And how we're doing this will continue to evolve over the next years. I think I'll leave it here for now. And if you have questions, I'll do my best to answer them. But with the small safety hat here, that I'm not Maria, and I may not know exactly what the full picture. Let's see.
Yeah, thank you so much, David. I mean, you should all know that David knew basically this morning that he was going to give this talk. So thanks a lot.
Yeah.
So maybe we have time for one or two questions, if we have any in the room. I just ask you to kindly use the microphones that are in front of you so that the people online can hear you as well. Do we have any? No. Oh, we have one question here.
So considering the filtration process that's happening during the collisions, how high or low are the chances that an important event is actually filtered out by mistake?
I can't answer that, to be honest with you. The filtering mechanisms are unique to each experiment. And of course, there are higher level ones as well, as things are sent. But what I've introduced here, the level 1, level 2 triggers and filtering, these are decided on by the experiment experts. Mm-hmm. So for example, a lot of times, an example of a level 1 trigger is noise or something that is known. So like if you have a silicon photomultiplier or let's say a classical photomultiplier tube, they generate some noise and heat that is not related to a physics event, but in any case may be recorded on your signal in some way. This can be thrown away. In general, it's up to the operators and the people involved in the experiment to make that call. Of course, we want to record everything we can, and we keep as much as we can because, I mean, if you find, let's say in the future you find some signal where there shouldn't be a signal, the first thing you're going to do is, okay, you've convinced yourself that, okay, there's excess energy here that's not explained by any of our models. If this is really something, if I convince myself this is real, then it has to have been there the whole time. So you want to be able to go back through all of the history over the past decades And you should still see this phenomenon there if it's something that's new and unique, and because it's a true new phenomenon. So yeah, absolutely, we can't be so carefree in throwing away stuff that is that we think is just noise. You need to keep a reasonable reasonable set. But yeah, to answer your question, the way that this is decided is unique to each experiment and to each, let's say, subdetector on the experiment. So,
Thank you.
Okay, so unfortunately we don't really have time for any more questions because there's a new meeting that has to use this room. I would just like to remind you of the event today. If you go on your computers, you can follow this live. The launch of this run of LHC. And then at 5 o'clock, there will be the summer student welcome drink. And that takes place in Restaurant 2, just across the street. And I would just like to say goodbye and thank you to those who connected online as well. We'll see you at the next lecture, which is taking place this week again. I will send out a reminder again.
I'll use my last second here to promote the CERN Music Festival coming up. Go to it. It's a good time. It's live music, food. There's a shuttle bus that takes you there and back. Enjoy it. Thanks, guys.
Thank you. Bye-bye.